In this video, we're gonna talk about fiber bundle and the homotopy lifting property. So let us first motivate this. Let's motivate this with the need to compute homotopy groups using long exact sequences. So remember when we were doing homology, a key tool in computing homology was using long exact sequences. Every homology theorem must satisfy the homology axiom, so in particular, it must give a long exact sequence for every pair of space. This long exact sequence, though, involves relative homology groups. We can, however, turn it into a sequence of absolute homology groups if we use excision to relate the relative homology group with the reduced absolute homology group of the quotient. Thus, we see that a short exact sequence of spaces leads to a long exact sequence in homology. Now, how about homotopy groups? Well, for pairs, we also have a long exact sequence of homotopy groups, and here this also involves the relative homotopy groups. The question now is, when we have a short exact sequence of spaces, can we also just use excision to get a long exact sequence in homotopy groups involving only absolute homotopy groups, so no more relative homotopy groups? Unfortunately, the answer is no, because we no longer have excision in the case of homotopy groups. However, we can remedy this. If instead of looking at quotient map, we look at fiber bundles, or more generally, maps that satisfy the homotopy lifting property for disk, then these homotopy groups, these relative homotopy groups, are going to be isomorphic to this absolute homotopy group. And thus, we will indeed have a long exact sequence in absolute homotopy groups. Thus, a common technique in computing homotopy groups is to look at fiber bundles and then compute using the long exact sequence associated to them. Okay, so what's a fiber bundle? What's a homotopy lifting property? And why do we have this long exact sequence? Let's first look at what a fiber bundle is. To motivate this, let's think of the algebraic way of thinking about quotient. If we call this quotient map P, then we can think of every point x in this quotient as the collapse of the fiber P inverse x. We can then view this space x as just a collection of fibers of both points in this quotient. So that's the way we should visualize a fiber bundle. Over every point letter x in this base space, we will have a fiber P inverse of letter x. However, unlike with fibers in the case of a general quotient, we are going to be more demanding on these fibers of a fiber bundle. We are going to require them to look very similar locally. That is, there has to be some fiber space F such that around every point letter x in X we must have a neighborhood U over which E just look like a product of U with F. This is called a local trivialization of E. So locally, E just look like a product and this map P just look like projection. All the fibers are gonna look like F. Let's look at a few quick examples of fiber bundle. The cylinder, for example, is a fiber bundle. It's actually a trivial bundle because it's globally a product. The fibers in this case are all homeomorphic to the unit interval I. Alright, now let's look at a non-trivial example, the Mobius span. We can view the Mobius span as a fiber bundle over its middle circle here. As you can see, the Mobius span is not globally a product, but locally it does indeed look like a product. The fibers in this case are again all homeomorphic to the unit interval. In this model here, the base space is this circle, and we can see that locally, the space looks like a product with fibers being the unit intervals. If we identify the other edges of the Mobius span, then what we get is the Klein bottle. And it again is a fiber bundle over its middle circle, but in this case, the fibers are actually circles, because these points are identified. And you see, even though globally this is not a product, locally on an interval, this looks like a product with fiber S1. Now, the next very important example is that of covering spaces. In that case, the fibers are gonna be discrete set. This example is important because we can think of it as inspiring the key property that we want from our fiber bundle. This is a property that will allow us to convert from relative homotopy group to absolute homotopy group, and thus gives us a long exact sequence in absolute homotopy group. To understand this, let us review path lifting for a covering space. So let's say we have a covering of E over X, and let's say we fix a base point x0 and a base point e0 in the fiber over x0. Now recall that we can view elements of the fundamental group of X based at x0 as paths in E starting at e0, because every loop in X based at x0 lifts to a unique path starting at e0. Note that if we let F denote this fiber, then this lift must end in F. Moreover, homotopic loops lift to homotopic path, so this gives a well-defined map from pi1 to the set of paths starting at e0 up to homotopy. Now this can be thought of as the relative pi1. So this theorem that we want to prove here is just the generalization of this statement. And here, for us to be able to lift path, the key thing we use is that homotopic path lift to homotopic path. A generalization of that is the homotopy lifting property. And we'll discuss that in the next video.